This video will demonstrate how to use Stata to conduct a dependent or paired samples t-test. To illustrate this example, we're going to use the growth and enhancement of student data from the Montana Office of Public Instruction. And so you can see I have that data open now based on this message in Stata. And then I can go up to the data browser and I can look at this data. And so for this particular example, because we're comparing the same individuals twice, from pre to post, if you will, we're going to use the dependent samples t-test. In this case, our before measure or our pre-test measure will be their 4th grade math scores on the criterion reference test, and our post-test measure will be our criterion reference test scores on the 8th grade math scores. So we want to see what kind of improvement students have made over the course of 4 years. Now when we do a paired samples t-test, like the independent samples t-test, we need to explore our data a little bit, and we need to test the assumptions of the data to see if they hold for conducting the t-test. And so the first thing I want to do is get a graphical representation of our data. And so I can do that by producing a histogram of the 4th grade math scores. And we can see that this data is negatively skewed. In other words, most of our frequency of data points are in the upper higher end of the distribution. And I can save this, and so I'm going to save it as math 4th, and I'll save it to my desktop, because when I produce my next histogram, what's going to happen is that this is going to be overwritten. And so I'm going to produce a histogram of math 8, and we'll look at that. And we can see that the math 8 scores are basically the same. So the 8th grade math scores look very similar in terms of being very negatively skewed. And so I'm going to save this as math 8 to my desktop, and then this is saved, and then I can go ahead and open up I'll go ahead and open up my math, my 4th grade math, and then I can toggle back and forth and see the 4th grade math and the 8th grade math. And so this kind of gives you an idea of the distribution and what it looks like visually. However, we really want to be more precise in our tests of the normality of these two distributions. So one of the things we can do is we can go to Summary, and we can go to Distributional Plots and Tests, and go to the Shapiro Wilks test, and we can look at 4th grade math and 8th grade math, and then we can go ahead and get a result for the normality. And so we can see that for the 4th grade math variable and the 8th grade math variable, that these are significantly non-normal distributions. So we have violated that assumption. However, there's one other assumption that we need to check, and that's the assumption of equality of variances for the 4th grade math and the 8th grade math variables. Now we can do that by going to Statistics, Summary, Tables and Tests, and then Classical Tests of Hypothesis, and go to the Variance Comparison Test. And in this case, we have 2 samples that we're going to look at in terms of our variances. The first is the 4th grade math, and the second is the 4th grade, or the 8th grade math. And then we can go OK, and we can look at our results here, and you can see that we get the means for each variable and the standard deviations. They don't give us the variances, but really the standard deviations are indicative of our variances because the standard deviation is the square root of the variances. And what we're testing here is that the ratio of the 4th grade math variance or standard deviation to the 8th grade math variance or standard deviation is approximately 1. In other words, one is not much larger than the other. And so to look at this statistically, we see that if we were to reject the null hypothesis and accept the alternative hypothesis and say they were significantly different, our type 1 error rate would be very high. It'd be 32%. So because this is above 0.05, what this means is that these the variability or the variances, the differences in variances are not significant, and we can go ahead and proceed with our t-test to compare the 4th to the 8th grade math scores. So we can go up to statistics, and again we'll go to classical tests of hypotheses, and then we'll go to t-test. And in this case we're using a paired sample t-test. And our first variable, what I'm going to put in is 8th grade first. And the reason I'm going to put that in is because it has the higher mean. So we want our outcome to be positive, even though we interpret the absolute value of that difference. And then I'll put in 4th grade math, and then I'll go ahead and go OK. And so we can see that for the 300 observations, that the pre-test or the 4th grade test for math was 274.106. That's the average. The mean for the 8th grade math test was 276.43. That's a difference of 2.32 on average score points between the two testing times. And the standard error of the difference scores, or I'm sorry, the standard deviation of the difference scores was 18.56 if we round off. Now, our research question was basically implied was is there a change from pre or from grade 4 math to grade 8 math on the criterion reference test? And we can see that this change over time, this 2.32 average difference, was significant because this probability is below 0.05. So there's only a 3% chance that we make a type 1 error if we say that this difference between these two groups is significant. Now, even though this result is significant, it's somewhat small. So what we can do is we can look at the effect size or the practical significance for our dependent samples t-test. And to do that, we simply subtract the 8th grade mean from the 4th grade mean and divide it by the standard deviation of the difference scores. And by doing that, we take this ratio, and our ratio is 0.12, the value of that ratio. And so what that means is that our 8th grade mean is about a little over 1/10 of a standard deviation above the 4th grade mean. So although the result is significant, that result is a small in magnitude.